let's move to B part 8, miscellaneous tips on applied math and physics. You see, before I'm doing lecture 1, I would like to tell you I'm quite motivated on my work, and I please comment, share, give a like or dislike, which is very important for this channel, okay? And don't forget to review the 343 videos. You see my message, which is a very basic. Only I'm worried about this case, the applied math for mechanical engineering, physics, civil engineering, and the area of electromagnetism and so on. After that, we will move to the theory of relativity. Okay, so all these subjects are important concepts that I'll be using in, again, mechanical engineering, civil, and physics. You see, and also as a basic concept that we'll use in the theory of relativity. But now I'm worried only, okay, and applied math to engineers and physicists. Now, and please share and comment, okay, which is very important, okay, and I will appreciate some comments will really make me more motivated to do this work. Now, points and curves on a manifold, lecture 1. A manifold M is just a set of points, each labeled by coordinates xi. These coordinates are local labels, okay? They don't carry any motion, the notion of point, a position, okay? And unless you embed M into some external space. You see, this here is external space. This point here, this is not position vector, okay? That's a big distinct difference between extrinsic and intrinsic geometry. For instance, if you have a surface like that, okay, a sphere, okay. Now, if you have, for instance, a bird flying outside over here, okay, then I set a position vector, and this point over here, I can calculate derivatives, okay, tangent vectors, normal vectors, and so on. But if you walk on the surface over here, okay, and measure, for instance, temperature at each point, okay, then I call each point is a label, okay, so you don't add temperature on different points, okay, that's why you cannot find derivative at a point. And all these points here, all these labels, they are distinct, okay, they don't depend, okay, one of the other, okay, so they are apart, they are points, they are labels, okay, and that's why the first concept about intrinsic geometry, okay, don't confuse with the extrinsic geometry. This case we have a point, okay, I set a position vector at each point, and this point in the extrinsic geometry I can derive, I get tangent vector, normal vector. But on this point, on this surface, okay, you can't do that. Okay, that's a big difference between geometry, intrinsic and extrinsic. Now, in this case over here, okay, then the external space is just, these are real numbers, this is lambda, between a small interval minus epsilon and plus epsilon. this, I know this map over here, gamma of lambda 0, then I reach point P, which belongs to the manifold. And also, I can have a lot of values, okay, of lambda, and apply the same map and get a curve over here, okay? Again, each point over here on the manifold, each point is a label, okay? Is a label. Now I put a flag on each point over here, okay? I have numbers, but these numbers is like I said, like temperature, which I'm measuring at each point. Now, gamma of lambda, each point is a label. Again, there's a curve, okay? Gamma of lambda, okay? I just, in this case, I vary lambda from minus epsilon to plus epsilon, okay? There's a very, very small interval. This belongs to the real. Now, it's clear here. Now, let's capital Xi, gamma I of lambda, be the external space, this external space over here. So I will give you an example, this a numerical example, just to clarify what I'm saying. Now, capital Xi is just lambda plus 1/2, lambda plus square root of 3 divided by 2, and lambda square. This is, attention now, this is R3, okay? Attention now, this R3. Now, capital X represent the R3, the Cartesian coordinates. Now, let's set lambda 0 is equal 0, okay? Lambda 0 here is equal 0, just to obtain point P, okay? So, this is 0, and this is 0. So, this leads to 1/2 square root of 3 divided by 2 and 0. This is the coordinates, attention now, the Cartesian coordinates, okay, which I created, okay? This over here is 1/2 square root of 3 divided by 2 and 0. So that I have coordinates, okay? I set Cartesian coordinates at point P, okay? That I denote a capital X. Now, the coordinates label are, in this case, this is a label, okay? Small x1, 1/2 square root of 2, 3 divided by 2 and 0. This is labeled, okay? Correspond to these created Cartesian coordinates. Now, I want to construct a chart. Chart is a very important concept, and in the literature in general is quite confused. So I will show you how to calculate, to construct a chart belongs around this point P, okay? First of all, I have to get, okay, a map I call alpha, okay, with convert point P to point Q. Attention now, point Q is the same point P, okay, the same location. I just move it to this here, just to be clear, more clearly. So this U1 and U2, they are coordinates, again, Cartesian coordinates, okay, in which I obtain point Q using alpha, okay. Alpha could be a map, it is a map, could be a matrix, or I can create, this is called a fantasy, okay? I can create any fantasy, okay? Just, in this case, varying alpha, okay? But this here, okay, I don't use as a map, I don't use the matrix, I just use this relation over here, okay? Phi and theta. Phi is U1, this will be U1 and U2, just I call phi and theta. So this here, I impose this fantasy here, okay? I choose, in this case, this fantasy over here, then I have the relation between in this case, between this coordinates and this fantasy over here. Okay, could be, for instance, sine square, cosine. In this case, could be sine 5 and tangent theta. Doesn't matter. Okay, I just chose this one. So here, in this case, this particular case, I divide x2 by x1. I cancel sine and I get tangent of theta, which theta will be square root of 3. Theta is equal pi over 3. Tangent theta is square root of 3 implies that theta is pi over 3, which I call U2. Likewise, cosine phi is equal 0, phi is pi over 2 is 1. Attention now. From point P, I calculated point Q. Okay? That's important. That's for you to understand how to construct the chart. Now, since I have this relation here, okay, now I can move back from R2 to M. That's important, okay? So I can choose many points around Q and map back. You see alpha minus 1 here, and map back to points around P, okay? That's why I construct a chart U. I call here chart V, okay? That's important. That's a region close to P, this one. This region close to Q. You see, that's very important here for you to understand. I'll repeat, okay? I'll repeat the steps. First of all,